afternoon. I want to show you a neat way of using truth tables to solve some knight and knave problems. So these knight and knave problems are a traditional type where somebody, if they're a knight, always tells the truth. And if they're a knave, they always lie. Some typical sorts of problems, you might walk up to one of them and you don't know if they're a knight or a knave and ask them some questions and see what the response is. Now, if, for instance, you walk up and you say to one of these two people, not knowing who is who, and one says, we are both knaves. You would have some choices to make. You think, well, could that be true? Well, if he says a true statement, then person B here would have to be a knight. So if they're both knaves, then B is a knight. Well, we can't be a knave and a knight, so clearly this cannot be true, which makes B have to be a knave. And then you could go back and say, well, if B is a knave, then he lied to me. They are not both knaves, you liar. Which means A couldn't be a knave, or else Mr. Liar would have told the truth. So A must be a knight. So there's a way of describing things and solving these by talking about it. Now, what we could do, likewise, is introduce a little bit of symbolism, symbolic logic, and make a truth table. So, for instance, if somebody is a knight, then they will say something that's true. So the way I would phrase this is, imagine the knight. They're going to say something that's true. And if they said something true, you would know they're a knight, because there's only two options, a knight or a knave. So this tells me somebody's a knight if and only if they say a true statement. Likewise, if they're not a knight, that is a knave, then they must say something false. In our symbolism, we might say, K is a knight if he says something true, and they're not a knight if they say something that's not true, false. That will be helpful in our truth table. Now, a couple other things that will be helpful is remembering or learning some notation, where the word and, which could also be we are both, could be given by either the symbol of the ampersand. Sometimes it could also be given by the symbol that sort of looks like a caret in the sense of capital 6 on your keyboard. The word or sometimes is given by, say, the union or something that looks just like a V. The reason these happen is in logic, the and corresponds to what's true about both things. So that little in between, so that's close to this little pyramid shape, right, the capital 6, which means kind of like the intersection. And or means A or B or both, so the whole thing. Okay, so we're going to use that logic, that Boolean logic, to solve some of these problems. So let's see what would happen if we program these ones. So this statement, we are both knaves, was made by B. If I wanted to write that as a statement with logic, I would say it this way. So B said, so B, can use some arrows, said we are both knaves. That means A is not a knight and B is not a knight. That's what B said. So just to be careful, they're going to have us do parentheses as much as possible. Either that way, I believe actually, let me just double check this, but I think they'll be okay with this notation as well. So what the truth table will tell us is, if B is a knight, then this must be a true statement. If B is a knave, this must be a false statement. Let's plug it in. So here we have a website that will just generate a truth table for us. I simply Googled truth table generator, and here's what I got. So we want to put in that statement. So B, if and only if. Now they give us some shortcuts on the keyboard down here. So if and only if looks like this for this program. I'm going to use some parentheses here so they know what we're talking about. So person B said, we are both knaves. So A is a knave, so A is not a knight. So I put the little squiggle, so not A. So A is not a knight. And in this case, I've chosen to use the and symbol. I could have used other notation. And B is not a knight. So let's hit generate truth table. And look what happens. So it will give us a lot of things. So it says, it goes through all the cases where it's saying, well, what if A is a knight and B is a knight? What would happen? This would read, well, if B is a knight, then it's true B is a knight. And this relationship is false. What that means here is that the right side over here turns out to be false. So it goes through all these different cases, and what I'm looking at is in the red, which one of these is true? And only this one in the middle. So this statement that B made is true in the sense of consistent. Either B is a knight and this is true, or B is a knave and this is false. So either, in this case, it's T and T, so true and true, or false and false. So B lied. So this tells us that A would have to be the knight and B would have to be the knave, which is exactly what we found. But notice here it does use that vacuous sense of true. True here just means B was a knave and he lied. That was expected. It was consistent. So it's not that B said a true thing, right? Because remember what B said. B said we are both knaves. He lied, but he is a knave. And so when we say that statement works, it says if B is a knight, then we are both knaves. It's false that they're both knaves, and it's false that B is a knight. So the false implies the false. And so there's this strange sense of truth sneaking in, and it's practical here. Let's see how this works for a slightly more complicated one. So we're again encountering a few knights. In this case, their names are Sue and Zippy. Well, they're knights or they're knaves? Let's find out. So Sue says Zippy is a knave. So Sue is going to tell us that Zippy is a knave, so Zippy is not a knight. So Sue says Zippy is not a knight. But Zippy says both I and Sue are knights. So that would be Zippy and Sue. I just forgot how to do that simple. All right, did it backwards. Zippy and Sue are knights. Let's stick this into a little truth table generator and see what we get. So Sue says Zippy is not a knight, comma, space, and Zippy says both Sue and I are knights. Oops, excuse me, one of my formulas is not well defined. Oh, here we go. They did not like those parentheses there. So in this case, we're going to go through and see, well, which of these work. So notice it's going through all the cases. So it says if Sue and Zippy are both knights, then Sue's first statement is false. So when Sue says Zippy is a knave. Okay, so this can't work. Next, it says, if Sue is a knight and Zippy's a knave, then her first statement was true, and she's a knight, so that makes sense. And then Zippy was a knave in this case. So the knave lied, because this is false over here. Therefore, this is consistent. So the knave lied, so that's why it says this is true. It's the vacuous sense. So there's a T here and a T here, and that's the only row that has two true or consistent statements. Therefore, our solution is Sue is a knight, true Sue is a knight, and it's false, Zippy is a knight. So Zippy must be a knave. And this can be used if you have 100 people on an island saying various things about each other. And so that's one of the nice things about this technology. And again, I'm going to point out the truth here is that vacuous sense based off of that original statement. You know, Zippy is a knight if and only if Zippy and Sue are knights. Well, as we go through the cases, it's false Zippy's a knight, and it's false Zippy and Sue are knights. And so that is consistent. So we say true in that vacuous